Good evening, and thanks for joining tonight's TI Technology webinar hosted by Texas Instruments. For tonight, we're going to deal with some computer science resources to get you ready for fall. My name is Mike Houston, and I'm the moderator for this event. I teach algebra and calculus near Pittsburgh, where I use TI Technology to make tough-to-teach, tough-to-learn concepts accessible to all my students. Tonight, I'm really excited to be joined by our three panelists, Tony Norrell, Michelle Reinhardt, and Alice Fisher. Tony has over 25 years of teaching experience from 5th grade to college algebra. She works as a math specialist and as a T-Cube regional instructor, and she is a recipient of the Presidential Award for Excellence in Math and Science Teaching. Currently, she and Michelle are developing and delivering computer science professional development in Texas. Tony, so great to have you with us tonight.
Thanks, Mike. I want to let everybody know that I'll be monitoring the chat tonight and asking questions. So everybody feel free to comment and get involved in the chat screen.
And born and raised in rural Ontario, Michelle studied mathematics, physics, and education before moving to Texas. Michelle has taught high school math and science at rural districts in Texas, while also working as a math and science consultant throughout the state. Her interests include technology integration, conceptual understanding, and curriculum and instruction. Michelle, thanks so much for joining us tonight.
Thanks, Mike. Glad to be here.
And lastly, Alice is a computer science and mathematics teacher, currently teaching AP CS Principles and AP CSA at Bel Air High School in Houston, Texas. Since 2008, she served as instructional coach and master teacher for Rice University School Mathematics Project programs, and is also a T-Cube regional instructor and a Code.org CS Principles facilitator. She is happily married with one lovely daughter and 2 dogs, and loves to hike in the mountains. Alice, thanks so much for joining with us. Alice, thank you so much for being with us tonight.
Thanks, Mike. I'm really excited to be here.
We're expecting a large crowd, so your audio is muted. Feel free at any time to send questions to Alice, Michelle, or Tony using the Q&A window on the right side of your screen. And like Tony already mentioned, we're going to be using that chat window to send general messages. As a reminder, the session is being recorded, and we'll provide a link to the event certificate of attendance, as well as a link for the documents that are being used tonight at the conclusion of the webinar. Once that recording is available, that's how we'd love for you to follow along. That way you can really go at your own pace, pause, and rewind as necessary. We hope you don't have any audio issues, but in the event that you do, try selecting Communicate from the WebEx menu and choose Audio Broadcast. At this point, Michelle is going to discuss our agenda.
Thanks, Mike. So Mike already took us through the first part, welcome and introductions, So then the rest of the webinar is going to be like a blur of all kinds of resources to help us think about how we could integrate computer science into STEM courses. So we're going to start by looking at a little bit of coding on the 84 and Nspire platforms. We'll share the 10 minutes of code activities with y'all. Then we'll look at some examples of coding the Innovator Hub. Then there are other activities for extending that work with the Hub, including some STEM activities and Path to STEM projects. Then Alice will take us back to coding on the TI Innovator Rover, which we're so excited about. And then we'll wrap up by sharing some other ways that you can continue the conversation and continue your professional development around these ideas. One other thing I might share on this, as we share links, I know Tony will be sharing a number of links in the chat throughout the webinar. Feel free to open those up in other tabs in your browser and have them available to revisit later after the webinar.
Thanks so much, Michelle. And Tony is going to discuss our expected outcomes.
Thanks, Mike. At the end of the session, you will have explored classroom activities for teaching and learning computer science, engaged in computational thinking practices, discussed opportunities to continue the conversation and further grow your knowledge, and applied fundamental computer science topics and structures to solve problems.
Thanks so much, Tony. Michelle, you have control. And Alice, feel free to start. Yep, you're good to go.
Great, thanks, Mike. So tonight we're going to delve into the connection between computer science and STEM, and as we've mentioned, share lots and lots of resources that will support both STEM and computing. So we really want this to be an interactive session, so we're going to start with a question. How might integrating computer science support STEM teaching and learning, whether it be mathematics, engineering, science? So we're going to ask you to think and then share in the chat.
And while you guys are all thinking, as you're sharing in the chat window, I probably should have mentioned this a minute ago, but there's a send to option. And we want you to send your responses to all participants as opposed to all attendees. If you send to all participants, everyone tonight will see them, all the panelists and all the attendees. So please feel free to send to all participants in the chat window. Thanks.
Thanks, Mike. And I can just kind of start off the conversation. Oh, I see a comment. And actually that is something that I was going to mention myself, was this idea of problem solving and going through that struggle and really focusing on that process of problem solving. Okay, and we'll give you another few seconds to chime in. So absolutely. Critical thinking skills and methodical and logic problem solving as well. So feel free to keep typing, but I would love to have you think of this question throughout the webinar. This is really our underlying theme, how computer science supports STEM learning and teaching. So just keep this question in the back of your mind. So we're going to go ahead and dive into a problem now. Many of us teach applications of the Pythagorean theorem. So let's go ahead and demonstrate how to create a program that will compute the hypotenuse of a right triangle. So we're going to go through the steps on how to code this algorithm on the TI-84. So as we start coding, we're going to need to create a new program. So we're going to go to Program, and then you're going to scroll over to New and Create New. And let's go ahead and name this Pythag. We've got a limit of 8 characters here, so we'll keep it short and sweet. And in general, we want to clear the screen at the beginning so it looks nice when we see the output. So we're going to go ahead and go to Program. And you're going to be presented with some menu, some categories. And because we're interested in the output, we're going to head over to I/O, which is input output, and let's go ahead and clear home. That's going to give us a nice blank slate at the beginning. Okay. And when a user is going to run this application, you'd like to share with the user what the program actually does. So we're going to go ahead and go back to Program and go back to I/O, and we want to display output. So that's going to be choice number 3. And we can say something like, you know, this program will compute the hypotenuse. Okay. And, or just some abridged version of what it's going to do. Okay. So Michelle is kindly typing for me so I can kind of talk and focus on what I'm saying. And we're going to use a couple display commands so that it looks nice and it won't run off the line. So we'll do a couple more. Another second display statement will compute hypotenuse. All right. So now you actually want this program to accept input from the user. So we're going to go ahead and tell the user what we want them to enter, which kind of input. So in order to compute the hypotenuse, we're going to go ahead and, again, use a display statement and just write. And notice that Michelle is using quotes because we need to type in some strings, which is just a sequence of characters. So we're going to display enter the legs. And now we need to use a command that will actually accept the input from the user. So we're going to go back to program and go back to IO. And then we're going to go ahead and ask them, prompt them. So we'll use command number 2. And we're going to store those in 2 variables. And the 2 variables that kind of make sense for the Pythagorean theorem are going to be A and B. So let's go ahead and type that in. So at this point, we're going to have 2 values, okay, A and B. And now we need to actually display the output, which is going to be the hypotenuse. So we know what the how to compute that. It's going to be the square root of a squared plus b squared. And we want to store that in a variable. Now, we're going to use the get, which is store, which is right next to the 1. And of course, we'll use the letter C or the variable C to store that. And then the last thing we'd like to do is go ahead and display the output, the result of the computation. So we'll go back to IO and display. And then we can display hypotenuse equals. And then we can also add a second argument here, which is going to be C. So now when we run the program, there's actually a shortcut. If you take a look at the very top of the screen, it says Edit Menu Alpha F5. This is the recent addition with the newest operating system. So if you haven't updated your TI-84, I encourage you to do so. So let's go ahead and press Alpha F5. And notice that there are now some editing options here that weren't previously available. And not only do we have these other options, we can run and execute the program directly from this editor. So let's go ahead and press 1. All right. So now enter the legs. We can enter in our Pythagorean triple, 3 for A, and then 4 for B. And then if we press enter, we'll get our hypotenuse, which was 5. Now, suppose that you want to get a little bit deeper into some of these, this idea of computational thinking, and we want to create a program that's a little bit more flexible. A lot of times we'll ask students, not only do we want you to compute the hypotenuse, but what about if you're given the hypotenuse and a leg, then how can you compute the leg? And have a program that's flexible enough in order to be able to handle that, okay? So here is a slide, and this shows Pip's leg or Pip's leg, however you pronounce it, and it looks very similar to the program that we just coded. So I'm going to give you a minute to kind of take a look at the program and make a prediction. And feel free to type it in the chat box of what the output would look like. We've got a new command at the bottom, output, and you can take a guess. It looks like it's accepting 3 parameters. So I'll give you a minute to just kind of take a look at it and just make a prediction of what this does. Okay, and then let's go ahead and you may have a mental picture of what this program, how it's different from the one that we just coded. So we can go back to the Smart View, and we're going to actually go to the home, we're back at the home screen. And another way to run the program, the standard way, is to press Program from the home screen. And Execute is the first menu item here. So we're going to run Pip's leg number 4. And if we do and press Enter,
So,
okay,
Alice,
and then yeah.
So I hear people saying things like, looking at this output command, that it's going to display the particular location on the screen.
Let's go ahead and see if that happens. So let's enter the leg and see what happens and the hypotenuse. So we'll enter 3 and 5, and then let's see what the output will look like. All right, so yeah, absolutely. It looks like we had leg equals, and in the previous program we had 4 on a different line, and in this case it looks like it's right next to leg equals. So absolutely, the first parameter gives us the row number, and then the second parameter actually gives us the column. So notice that leg equals is 4 characters, and so with the output 5, it told basically told the graphing handheld to place that 4 right next to the equal sign. That's excellent. Yeah. And now we want to create an even more complex problem. So we're going to show you a program called, well, first let's go and show piship. I'm not sure exactly how to pronounce that, type, piship. And this should look pretty familiar. So this is basically what we did for the first program, PyFag, but we went ahead and used those new commands that we demonstrated for PyFlag, the output. And notice that instead of 5.5, we have a 5.12 because hypotenuse is a pretty long word. And so next what we're going to show is PyFag 2. And I'm going to give you a minute to take a look at this program. Okay? So what's going to happen when we run this program? You can either kind of mentally think about it, or if you feel free to share on chat if you want to make a prediction and share.
Alice, while they're thinking
Yes.
about that, there's a question about why the 5, 1 when we did the
right. So the 5 represents the row number, and we will have had 4 output statements already displayed. And so if we would have put in a number less than 5, then it would have overwritten the output that was already on the screen. So we're keeping track of the number of rows. There's 10 total, and we had already displayed output on the first 4 rows, and so therefore we wanted to display the hypotenuse equal on that 5th row. Were there any other questions before we move to the predictions?
No, but I'm getting some comments about what this program does, the question
Oh,
that
great.
you asked. So they're saying that now the user is going to have a choice on either computing the hypotenuse or the leg.
Excellent. Yeah. And so this actually brings into this idea of selection as one of our building blocks of algorithms. And we've got an if statement at the bottom, which will allow a little more flexibility so that they can either compute the hypotenuse or the leg. So let's see if it actually works. And just notice before we move to running it that we're actually calling PyHeight and PyFlag within another program. So those are actually being called as subroutines. So this is just a really powerful way of being able to use a solution you've already created to create a more complex solution with a little more flexibility. So let's go ahead and run it and see what happens. We can go back to the home screen here and program and execute and then run PyFag 2. And then suppose I'm like, well, I actually have a problem. I want to compute the leg. Let's go ahead and press 1, R for response. Okay, so let's enter a leg. Let's say 3. Hypotenuse, let's say 5. Okay, and then we get leg equals 4. Let's go ahead and run that program again and let's try the other selection. Okay, so now let's go ahead and compute hypotenuse. Oh, here we go. Now we can actually enter in 2 legs, and we can enter in 3, 4, and we get our hypotenuse equals 5. Okay, so this is just kind of a little window into the power of programming on the TI-84. Even though it is a handheld, it does allow you to create more complex solutions and building on solutions that you've already created. Okay. Are there any questions at this point? We'll pause for a few seconds.
So there's a question about, can the subroutine program return to the original program?
So that's an interesting question.
And I wonder, subroutine program return, like almost a recursive call? Like, so if you had let's enter in PyFag2. Let's take a look at PyFag2. So at this point, we're calling PyFag hype. So is a question that in PyHype, can you call on PyFag2? Is that what the question is? I'm not sure.
Yeah, great question, because I'm thinking of 2 different things we could think about here. One might be if we could put in another display statement, like could we say something like, great, oops, I better spell it right, great job, and where after it runs the program from before, like after it runs one of those 2 choices, will it now return back here?
Oh, it should, absolutely, because it's sequenced. So let's go ahead and test it. This is an interesting test, so let's go ahead and run. Great question. Okay. And then we'll enter our 3, 4, and display. And there we go. Yeah. And so just notice that the great job actually entered the output. It was on line 4. So it did kind of overwrite what was there. Okay, and then we have it done. And another thing you might want to do is add pause, which is just allows you to kind of enjoy the results of the output at the very end before it gives you the done statement at the end. Yeah, with a pause. Perfect. That was a great question. Any other questions about that? And then while you're thinking, or we would love for you to reflect and share an algorithm that you could write a code for with your students, and if possible, share the course and the grade level, and just kind of see like what kind of interesting programs can you envision writing with your kids on the, or your students on the handheld.
Thanks, Alice. So we'll pause here for a minute and a half, and give everyone an opportunity to think about Alice's question and to share in the chat. What is an algorithm or a process that you could have your kids code out?
So I'm seeing law of sines and law of cosines in trig, and distance formula, slope formula, midpoint formula. Those are all great ones.
And this kind of brings us back to our first question about how computer science can support STEM teaching and learning. We hear a lot of algorithms from math. These are a lot of math algorithms, but hopefully science teachers, if you're participating, can envision some of the algorithms that you talk about in your class and how it could be supported by students writing these codes, because if they can code it, then hopefully they really understand how the algorithm works.
I'm getting some other ones on formulas for interest or earned savings.
Nice. Excellent. So I'm going to go ahead and let y'all read and think a little more, but We'd like to talk just a little bit about the resources that are also available to help you more specifically. So we're going to go to the education.ti.com, the TI codes webpage, and from there, there are lots and lots of great resources and online tutorials. So if we click on TI-84, which is the platform we just used, okay, and if you scroll down, you can see that there are activities for just basic coding and the innovator, and then there's Beyond Basics, which gets into a little more advanced topics, and Teacher's Lounge, which is where you can find the teacher and the student handouts and notes. So if you click on the first link, which is the TI-84 Plus family, the basics, click on that. So what we just did was we walked through Unit 2, and within a unit, there are usually about 3 skill builders that are exercises to kind of help you learn a little bit more on how to code on the handheld, and then there's an application problem. So if we walk through step 1, you'll see that this is basically what we just kind of demonstrated a few minutes ago was the Pythag, Heron's formula. Also is demonstrated the famous quadratic formula as well. So I've used this resource several times. A lot of times I'll code on the TI-84 and it's been a few weeks and I'm like, oh, how do I do that again? I'll go back to this resource and just say, oh yeah, that was in variables. It's a great online resource. So I think that unless there are any other questions, I'm going to go ahead and hand it over to Michelle. So Tony, are there any other kind of questions in queue?
Not right now, Alice. That looks great. I'm anxious to see the hub.
Oh, great. Me too. All right. Thank you.
Thanks, Alice. Also, after we finish up with the hub coding, we'll showcase where you can find PDFs of these same activities and student versions of those PDFs that you can download and use with your kids. So we'll come back to that idea in a little bit. So next, we're going to transition into exploring a device. Sorry, I got ahead of myself too. Let me go back over here for just a second. I want to show y'all what it looks like first before I just jump in and start coding. So we're going to transition into exploring this device, the TI Innovator Hub, that you can connect your calculator to for physical computing. And by physical computing, we mean writing programs that produce some kind of physical output, such as lighting up a light, using sound, motion, and or that accept some kind of physical input from the environment, such as brightness or other kind of factors. So with the Innovator Hub, you can code and control light output. You can turn the light on and off. You can use, you can color code a red, green, blue, or RGB LED output, lighting it up one of like millions of colors. And you can also control sound output to play notes and maybe even also some songs. You can collect input from the environment about the brightness of the particular environment you're in and then incorporate those measurements into your program. So a couple questions to keep in mind as we go into this next demonstration. I'd like you to kind of be thinking in the back of your mind, what kind of programs could we write that connect to the courses that we teach, whether those are math, science, computer science, or other courses. And also remember Alice's overarching question from earlier about how does computer science support STEM courses. So we're going to jump over to the Nspire platform, and we're going to learn how we can make sound with the Innovator Hub and then consider what kind of activities that might extend to. Earlier, Alice was showcasing coding on the TI-84, and everything she did there we could do here on the Nspire, and likewise, everything we're doing now in this part on the Nspire you could do on the TI-84 plus CE as well. So I'm going to create a new program, and I'll call it Sound. And you can't see it, but here in my office, my TI Innovator Hub is connected to my computer through a USB cable. So you can't see it, but you'll hear it in a minute. I'm going to go ahead and select a command from the menu, and specifically from the Hub submenu. And let's go ahead and send a setting. So I'm going to choose this first option to the hub. And we're specifically going to send a sound so that you can kind of observe the physical output, if you will. So the sound command requires 2 bits of information, a frequency for the sound we want to make. So let's say, I don't know, maybe 1,000 hertz, and the time we want the sound to play. So let's say 1.5 seconds for now. I can then run this code by selecting Run from the menu. So let me go find that. Menu, check syntax and store, and just a second I'll run it. But notice over here on the right side of the screen there's a shortcut, Control-R, and I'm going to use that shortcut later in the webinar as well. So I'm going to run this program, and let's observe the physical output of our program. So Tony or Alice, could you hear that?
Yes, that's a high note.
Okay, so I'll take that as a criticism, and so maybe we'll go back in here and say, like, can we change this frequency and maybe change it to, I don't know, like 750? Maybe that would be better. So let's try 750. We've lowered the frequency. I'm going to do Control-R to run this program. I'll run it again. So did you hear that one?
Absolutely. That was nice.
Okay. So you could hear the difference. So you could hear how, as we're kind of live coding this and changing that frequency, you can hear the output on my innovator. So with just this one line of code, we can make a sound, which is pretty neat, but like what else could we maybe do with this? And so there are a series of 10 minutes of code activities, kind of like what Alice showed us just for coding in general, that introduce students to many of these introductory coding skills for the hub, and then present students with some challenges and applications to apply these to. So we're going to actually quickly explore one of those together and see what we can kind of do in just a few minutes. So I'm going to jump back over here for a second, and we're going to consider a piano. And I'm pretty much a beginner in terms of all things music, so feel free to correct any of my language in the chat, or Tony and Alice, feel free to jump in as well. But let's consider playing notes played by a piano. So I'm going to just play some notes on this piano. And I wonder how we could code our hub to play kind of that scale of notes, all right? So that's what we're going to kind of think about next. So first, I'm going to share a few things that I've learned about music theory, and it won't take long because I don't know much yet. So first, one thing I have learned is that middle C, which I guess is this key on the piano, has a frequency of 261.6 hertz. So I'm actually going to start by creating a variable for the frequency, and I'm just going to call it F. And then I'm going to say F gets, and that's what this symbol represents in the Nspire coding language. And I'm going to assign F a value of 261.6. So give F an initial value of 261.6. Then we can tell our calculator, instead of playing 750, I want you to play the note, the frequency F. And I have to put that F inside an eval statement, as you see here, and that's kind of explored further in some of the other hub materials and also the hub webinars as well. So for now, we'll just kind of use that command in order to play that particular frequency for that amount of time. So I think now if I run this, you may or may not have been able to hear that sound. It may have been a little too faint.
We heard it.
It's that lower frequency. Oh, you heard it? Great. So it's a lower frequency than what we were looking at before. So that's just one note. But then here's another thing I've learned about music theory. There is a mathematical relationship between successive notes on the piano. So there's actually a mathematical relationship between this frequency and this one. And this relationship fascinates me. To get the new frequency, you take the current frequency, which is F, and you multiply it by 2 raised to the power of 1/12. So this is what we would do to get the next frequency. We would take our current frequency and multiply it by 2 raised to the 1/12. I'm going to add in this at the beginning of this command, which stores that new frequency back into the variable called f. So it basically overwrites f with this newer frequency for the next note. And so then we basically put the next note in, and so then we might say, oh, well, we could go do this again. Let's bring this command down, and let's send the sound again and play the new value of f for 1.5 seconds or whatnot. And we could repeat this again and again and again and kind of move up the piano or move across the piano to these different notes. But we may notice that we'll be doing the same things again and again. So another thing students will learn in computer science is that if we do something again and again and again, we could put those commands inside a loop. And so for this brief demo, I'll just use a for loop. And we could actually wrap these two commands of sending the frequency, of sending the sound with that frequency, and then increasing the frequency to the next value. We could do that again and again. So we could do that for maybe I starts at 1 and goes to 12. I don't know if that's right. We'll just kind of try it out and see. And that should happen then 12 times. I'm going to make a couple changes to this. Maybe I'll say, like, for time's sake, let's just play for half a second. And then I will also maybe right here put in a wait command and ask the calculator to wait for half a second. That will just let the previous sound play before the loop kind of cycles back again. So I always get nervous when we write code on the fly because maybe it works, maybe it doesn't, but let's try it out and see what happens. So I'm going to press Control-R to run this program, and my hub is over near the phone speaker. Let's see what happens. So what do y'all think? You can share some of your thinking in it? Did you hear it, Tony?
Yes.
Neat. So again, that's an idea of how we could take something kind of from environment or from music in this particular instance and think about how we could code it out on the hub. And that was just playing a scale, but we could also play a song using some of this theory as well. We could also think about some of the mathematics that's related to this idea. Here we're looking at like exponential functions or multiplicative patterns in order to just play music, which is really, really interesting. So let me show you where you can find this activity and others like it in the TI Innovator 10 Minutes of Code activities. And then, Tony, feel free to jump in with any other thoughts to add or other kind of things from the chat as well while I'm kind of navigating to that page.
Yes, and I've had some people comment that they could even put notes in an array and create a song and play it on the hub. So I think we've had some people that have gotten to try that.
Neat, so fun. That's one of our favorite things to kind of play with and think about how that works from a CS side of things. So Tony and I just shared the same link, so you have 2 copies of it. And so we are on the ball. So this takes you to TI Codes, but the Innovator Hub section of the website. And for right now, I'll go into the Nspire version because that's where we just were. And sorry, I have like the patience of a gnat. So then when that loads up, I'll go to Unit 2, and then I think we were just looking at Skill Builder 3. And so that will load up here, and then you'll notice that there's some information about music theory, about this 2 to the 1/12th, or the 12th root of 2 kind of idea, the information behind that. And then eventually it builds into the same kind of program that we just wrote together that will actually play out that scale or whatnot. So again, here's the digital version of that online, but then there's also a student version of it that we'll come back to later. So as we are kind of wrapping up thinking about just coding on the hub itself, I'd also encourage you to think about like what else could you do with that? What other ideas do we have for programs we could write with the hub, knowing that the hub can turn lights on and off, turn a light any color, output sound, can get brightness from its environment. I mean, what else could we maybe do or practice or write programs that would tie to our courses? So be thinking about that, and feel free to share some of that thinking in the chat. And while you're thinking about sharing that, I'm going to kind of show you some other options for this work as well. And we could even just use the hub to add sound and or lights onto some of the programs you talked about earlier. When you shared ideas for different algorithms you could write in class or whatnot, there might be lights and sound that kind of accent those programs as well. So as you continue to think about like what are some of the ways that we could integrate hub, I wanted to show y'all or have us think about this. We might have an idea for a program that requires additional output or input, like is it possible to collect distance measurements and then create a graph of those distance measurements? That might be something we do in either a math or a science classroom. Or what if we wanted to write a program that made an alarm type sound if the temperature was above a certain level? And so that could kind of act like a temperature warning system of sorts. So could we somehow collect other types of input measurements beyond just brightness? Maybe things like temperature with the hub, and or other different types of outputs that we could produce as well. And so that's where we want to go next, is to show you that there's actually a whole host of other accessories that expand the functionality of your Innovator Hub in that way. So here are some of the other input and output modules that are currently available. There's a servo motor, so you can actually program a motor to spin around or to connect to other things to create motion, a vibration motor, a white LED. There's also a light sensor and an ultrasonic ranger, and the ultrasonic ranger measures distance from things. And so wanted to kind of show you all that. And I also wanted to show you, because Tony, you just showed me this recently. I thought it was so interesting that there's a number of other modules that are coming out this spring. Let me kind of navigate to those for just a second. Right here, it kind of talks about like a temperature module is coming out, Hall effect sensor, temperature and humidity, moisture, all kinds of other things are coming late spring 2018. So that's kind of exciting to think about what we could use those for and what other kinds of projects and work that opens up for us. So as we're thinking about that and thinking about like what could we do with some of those things, I want to share with y'all just a few kind of snippets from, or a couple tweets, if you will, from Twitter. Let me pull some of these over for just a second. Sorry, I didn't want to move screens, pardon me, just a second. There we go. So this is a Tic Tac dispenser that some teachers made earlier this year, and they're using two kind of accessories here. There's a servo motor down under. You'll get to see it in just a second. So you can see that servo motor inside that's turning and dispensing the Tic Tacs. And then over in the other teacher's hand, sorry, kind of over here, he or she's actually holding a brightness sensor that they're covering up, kind of like the brightness sensors that are in, or like the motion sensors that are in like under faucets and under paper towel dispensers and things like that that are used to kind of tell if someone's there or not. So that's kind of another neat way to use these ideas for different STEM or engineering and or science projects as well. So I wanted to kind of show that one as an idea. Also, let me show you a couple others that I've got loading up, and as well as I wanted to mention the breadboard pack. So this is something that was really new to Tony and I before we started doing this work about a year ago. And the breadboard pack allows students to explore introductory electronics and how we can code circuit components. So sounds crazy, but many of these ideas are absolutely accessible to learners and show up everywhere in our daily lives. So just to show you a quick kind of example of that, here is a 7-segment display from a toaster. And side note, like my toaster is not fancy enough to have a 7-segment display. Yours might be, and or you see these 7-segment displays in all other parts of your life. But with the breadboard pack, you can actually code a 7-segment display and write a program that makes it run through different numbers or stay on this number for 20 seconds or whatever you'd like it to do. So the possibilities really are endless. I want to get back to Alice for her to share about the rover. So I'll just share 2 more links to in the chat. Actually, that's probably where I'll share them. But so I won't kind of show them on the screen. But there's 2 other sets of activities. One's called Path to STEM, and another one is Science Through Engineering Design. And these activities were so helpful for Tony and I when we first kind of started working with these other modules and with the breadboard pack, because they kind of walk you through step by step how you can do some of this work and how could we work with some of these devices, coding them through either the Nspire or the 84. So Alice, can I turn it back to you for talking a little bit about Rover?
Sure. All right, so the TI Innovator Rover is a really fun addition released just this year, and it's a robotic vehicle, as you can see from the image, and you can program it using either the TI-84 CE or the TI-Nspire. So the rover adds another dimension to the physical computing that the hub had opened up to TI handheld users, and we've seen a lot of examples that Michelle just shared. So let's go ahead and take a look at some of the components on the next slide. Okay, so you can take a look and see that there are different parts to this rover, and one I wanted to point to, which is really fun, is a mounted ranger on the front. Looks like headlights, but it's actually a ranger to measure distances to obstacles. So you can actually code your rover to avoid colliding into walls and people and your dog, and turn around and drive in another direction, almost like the vacuum Roomba, if anybody has seen that in action. And you can see it also has a marker holder so that you can physically draw shapes and designs by just kind of dropping in either a pen or a marker in that little area. So we're going to share a few videos, but before we do, I do want to take note that you do need the hub because your handheld will actually connect to the hub, and then the hub will actually connect to the rover. So those 3 kind of work together to code the rover. All right, let's take a look at rovers in action. So the first link is a video, a short video. It's my favorite selfie with a rover. And this was at a workshop that I led just a few days ago. This is Sarah, one of the T-Cubes instructors, and this is her and her rover that she received at the workshop. So I really thought that was a great selfie. And so if you take a look at the second one, this was at the same workshop. These are 2 participants, and they were racing their rovers to see which one coded it faster, and lo and behold, the teacher in the video didn't realize that he had created a command that paused, and then you had to press enter to get it moving, so he unfortunately was in second place, but they were having loads of fun racing and competing with their rovers. And so if you take there's a third video, and I call this a very festive video, or the holiday rover. And we mentioned that you can drop a marker into the holder there and draw lots of interesting shapes. And this one in particular drew a Christmas tree. So this is something you can do in December with your students. If you do have just one rover, this would be something fun to show them. So they are actually coding their rover to draw an evergreen.
And Alice, I want to jump in for just a second because someone shared earlier about how you could write a program to where rover could figure out angles and polygons or whatnot. So not rover, but the calculator itself. So like, why not then extend that to actually have the rover draw it out or whatnot? So I thought that was interesting.
Absolutely, and we're going to actually, they must have anticipated the next thing we're going to do. But before we do, let's share this last photograph. This is not a video, but it was a photo of the Coke snowflake fractal, and this was one of the most, I just couldn't believe that the rover actually drew this. It's a really intricate design, and it just shows what precision that the rover actually has when it is drawing its shapes. So I thought that one was really neat. I know, I wonder what the code looks like as well. Maybe we can code it together. So let's take a look at this next program. If we look at the code on the next slide, we're back on the TI-84 platform, and this program is called Predict. So we had Michelle earlier use the for loop when she coded the 12 notes in her scale and the chromatic scale. So we're going to go ahead and take a look at what this for loop does. So there's a hint. We've got a couple of prompts that will ask the user for some information. And let's stop here and see, what do y'all think will happen? Draw an equilateral polygon. Okay, let's take a look. So we're going to click on this. So this person had coded a similar program, and not sure what happened. Oh, there we go. And if you take a look, they're actually on a whiteboard. So they have a dry erase marker. And we can take a look. I'm not sure if y'all can see the polygon that it drew, but it ended up where it began. So at this point, what was the input? If we go back to the program, let's take a look at the variables here. Okay, we had S and we had N. So which of these variables do we know what the value of was based on the video? I'm not sure if you guys are able to see that closely. Exactly. What is S and what is N? It may have been hard to see. I think it was a hexagon that was drawn. Yeah.
So N is
so Jenny said there was 6. I'm sorry, go ahead.
No, that's what I was going to say, yeah.
And just to note, like if you do enter a number in, the unit that is the default for the rover is decimeters, which is interesting. So it's 1 unit is 10 centimeters, so it could have been about maybe 2 or 3 units. So anyway, we just wanted to show you just a little bit of what the rover can do, and again, there's limitless possibilities, just as with the hub. So if you're interested in learning more about coding the rover, again, we referred back to the 10 minutes of code. So if you go back to the root page, which was back even before there, and when we had the Teacher's Lounge being viewed, there was also a couple links. One was for coding the hub, and this one is it right here. And then there's also exercises to help you learn how to code with the rover. Okay, and if you go through, it's very similar to the basics of coding. You've got some skill builders to build up your skills, and then they have an application program, application project as well at the end.
Alice?
Yes.
There's a question. They want to know, do you use Innovator or Rover in your AP Computer Science Principles class?
You know, I have not this year yet. I actually just got a rover. I was able to get one at the T-Cube conference. So it's so new. I'm learning as y'all are learning as well. And I have some plans for next year. I only have one. And so some of my ideas that are kind of percolating right now is to maybe at the end of the year, especially in May, after the AP exam, we can kind of talk, kind of like what we did in this webinar, about an algorithm, and I can drive at the front of the classroom, but I can get input from the students, and then we can connect the rover to the handheld and the hub, and we can test our program. So the curriculum is pretty packed, but I can definitely see ways of integrating it next year, but I do have plans of sharing it after the AP exam, which is this Friday.
Great, thanks.
Wonderful. So in our last few minutes, I have just a final few activities or resources to share before we pass it back to Mike. So again, I'm pasting the TI Codes website into the chat. And this time I'm going to go into the platform first. So say I go into Nspire, for example. That's just the platform I've been kind of showcasing throughout the session. And specifically this time I want to take you to the Teacher's Lounge. And again, you could go to the same kind of site for the 84 as well. And so let's navigate to the Teacher's Lounge. And one of my favorite parts of the Teacher's Lounge, there's lots of great things here. One of my favorite things is the all teacher and student notes download. So I'm going to let that download on my computer for just a second. But what is downloading here are all of the teacher and student notes for the 10 minutes of code activities. So I'll open that up so you can kind of see what comes in that. And you'll notice that when I download that, I get all of the Innovator Hub, which includes the Rover, as well as the regular TI-Nspire files as well. So when I open that up, I've got all 5 units. So say, for example, I do like Unit 1, something like what Alice was showing us earlier. Notice that you have Word and PDF versions of everything for students and for teachers. And one of the main differences is the student version doesn't have answers, and the teacher version does. So you kind of have, here's a version you can hand out to kids and use right away, and then you also have the teacher version, which has some possible solutions to the particular problem or whatnot on it as well. So wanted to showcase that because that's kind of a one-place stop to get all of the activities that you could then work through. Last things to share, I will also kind of share in the chat that there are a number of other webinars that dig into these topics in more depth. And so there's a link now in the chat to the other kind of PD opportunities where you could go back and kind of work through at your own pace, more in depth about coding or more in depth about Rover or more in depth about Hub, each of these ideas kind of one at a time. Also, if you're on Twitter, we encourage you to join the conversation. These 3 hashtags, there's a lot being shared on T3 Learns, TI Innovator, TI Rover about the work that people are doing with these materials in their classrooms and how they could leverage them in support of student learning. And then TI's Twitter handle also is a great place to check out some other ideas. I think I have time for one more thing, so that would be that there are a number of summer workshops coming to locations across the United States. And so I'll link that into the chat as well. I think there are 4 or 5 Learning to Code workshops happening this summer as well. Mike, I think that's all we have time for, so I'm going to pause here and turn it back over to you. And as Mike kind of takes over, we just encourage you to kind of keep thinking about how integrating CS supports STEM teaching and learning.
Thanks so much. We're going to be in a very quick wrap-up tonight. To receive a certificate of attendance, go ahead and click that link in the chat window. Also, this is the link for the documents that were used tonight. If for any reason these 2 links aren't working for you, just hang tight because in a couple of days you'll automatically get a follow-up email. And that follow-up email will be a link to the recording, a link to the certificate, and a link for the documents as well. And if you're watching this on demand, go ahead and copy that link into your favorite browser to receive your certificate. Thanks so much, Alice, Michelle, and Tony for everything you shared tonight. I know summer's just around the corner, but it's definitely exciting to think about what is going to be coming this fall as well.
Thanks, Mike.
Thank you.
And thanks again, everyone, for joining us, and we hope to see you back online real soon. Have a great night.